So yesterday I said that transformations was one of our most important lessons. This comes next. They go together, they're very important. And 5.3 day 3 is about our parent functions. We have to have these memorized. You will have a memorization quiz on Friday. That's why I wanted to show it to you today. So then you had 2 days to study it. It's pretty much going to be a duplicate of what you see here. I'm going to give it back to you. Can you tell me what the parent functions look like and all that good stuff? Okay. So let's start with our first parent function, the constant. So it's technically f of x equals c. So it's f of x equals a number, or y equals a number. Now it can be any number, it doesn't matter, okay? So when you go to graph it, whatever number you pick, it would hit that number, okay? So as an example, let's do f of x equals 5. So that means that the answer is always 5. You should realize that this is a horizontal line. So at a height of 5, we would have a horizontal line. So a constant function is just horizontal. It is a function where a vertical line is not a function because it's x equals a number. Okay, now let's move on to our identity. Our identity function is the function f of x equals x, or you could also write that as y equals x. For many of these, you're going to notice that I plug in -1, 0, and 1. So even if you forget what the function actually looks like, you can always plug that into the function and use some algebra. If we plug in -1, the identity function keeps the identity of whatever you plug in. So that's why it's -1, 0, and 1. So it is our most basic type of linear function that has a slope that is not 0. So if we go onto our graph paper, spread your line across your graph paper. So your line looks something like that. So it goes through the origin, has a slope of 1. That's kind of like our perfect linear function. All other lines are built upon that type of line. Y equals mx plus b, f of x equals mx plus b is a derivative of an identity function. Okay, so it is just a simple type of linear function. So tomorrow or Friday, when you take a quiz over this stuff, you need to draw the graph, give me the 3 points that work, and the function. So like for this one, you would need to say this. For this one, you'll actually need to pick a number and then show me the points. So this, you'll need this, and you'll have to show me the graph, okay? Let's move on to quadratic. Our quadratic function is f of x equals x squared, or y equals x squared is also acceptable. We should know that that's a parabola. And so think about the fact that for our symmetry, if we were to plug in -1, 0, and 1, -1 squared is 1, 0 is our vertex, and then 1 is also going to be 1, because these two, because of the symmetry, should always match. But if you plug in a -1 squared, you get 1. If you plug in a +1 squared, you get 1. So hopefully that, just makes sense. Now, as far as the graph goes, I don't need perfection here, but I need you to at least go through those 3 points. If you want to be a little more accurate, you could also do, if I plug in 2, I get 4. So -2 is also 4. If I plug in 3, I get 9. So -3 is also 9, okay? So you can Draw me a parabola. Nothing fancy, but try to at least make it the correct width if you can. So go through 0, 0, negative 1, 1, positive 1, 1. I did do 2, 4, and negative 2, 4, 3, 9, negative 3, 9. You don't need those, but if you want to be a little more accurate, that would be great. Okay. Our cubic function, as implied by the name, that's going to be x cubed, or y equals x cubed. If we plug in the same lovely negative 1, 0, and 1, what happens to that negative portion of the graph? It stays negative. Negative 1 cubed is still negative 1. 0 cubed is 0. 1 cubed is 1. This function has what's called origin symmetry. It goes through the origin, but it's almost like a pinwheel. I could flip it around the x or the origin. What's in the first quadrant will end up in the third quadrant. If this graph had origin symmetry and it had a piece in the second quadrant, it would also be down in the fourth quadrant. So what I mean by that is here's like half a very steep looking parabola. This half, though, goes downward. But it's the same curvature, but a little steeper because you're cubing that number, because like 2 goes all the way up to 8. Negative 2 goes down to negative 8. But that's that same curve, half a parabola-ish looking thing, half a parabola going down. Okay, so that is our cubic function. So those are the quadratics and the cubic. All the function transformations we talked about in 5.3 day 1 can apply to any of these functions. If I do something on the inside, it's going to affect it horizontally. If I do something on the outside, it's going to affect it vertically. So our reciprocal function is f of x equals 1 over x. A little bonus piece that you could get on this function is if you tell me that that's the same as x to the negative 1, that's going to help us later on when we are going to be exploring functions with negative powers. So if you give me that little touch of information, I will give you a bonus point. For this function, if you plug in negative 1, you get 1 over negative 1, which is negative 1. If we plug in positive 1, you get 1 over 1, which is also 1. But if we plug in 0, it's actually undefined. That is going to be a vertical asymptote, which I need to see on the graph. So when we go to the graph paper, first thing I want you to do with this one is put a little dashed line down your y-axis, because that's a vertical asymptote. So the vertical asymptote is at x equals 0. So I expect to see that on your graph, okay? This graph also has a horizontal asymptote at y equals 0. I expect to see that on your graph, okay? So this graph does have origin symmetry as well. It has a piece here and a piece here. Let me show you how to draw them. If you plug in negative 1, you get negative 1. If you plug in positive 1, you get positive 1. That doesn't give you a lot of information. But let me give you some other points just to clarify what it's doing. If you plugged in a half, at the half point, you are at 2. At the negative half point, you're at negative 2. If you plug in 2, the flip of 2, the reciprocal of 2 is 1/2. So at 2, we're at 1/2. So just by plugging in 2, negative 2, 1/2 and negative 1/2, and you take the reciprocals of those, you get a more of a sense of what your graph looks like. But technically, we're going to head toward this asymptote without touching it, head to this asymptote without touching it, head to this asymptote without touching it, head to this asymptote without touching it. So think if we put a little push pin right in the center, and we rotated this 180 degrees. We turned it 180 degrees. This piece would mirror and get down to that same exact spot. It'll look like we didn't even touch the graph. And that's what the cubic function does. That's what our reciprocal function does. It has that weird symmetry. It's kind of a turning. I can turn it 180 degrees and I get the same thing on both from what I started with. So get yourself a little bonus point. Don't forget to put your vertical asymptote and your horizontal asymptote to get full credit on that graph. Okay. Now let's go to the square root function. The square root function is f of x equals the square root of x. Shocking, right? There's a bonus point you can get on this one if you write that as x to the 1/2 power. Now we've been exploring how our radicals can be written as fractional exponents. So that's just a good one to kind of get in your memory banks because of the fact as we head toward other things that will be helpful. We cannot plug in negatives for this. So instead of plugging in -1, 0, and 1, I definitely plug in 0 and 1, and that usually gives you enough information. But then I think about what are perfect squares that are also nice. So 4, 9, 16. 4 and 9 usually fit on my graph, 16 doesn't. But let's at least plug in 4. If I take the square root of 0, that's kind of my starting place. I get 0. If I plug in 1, I get 1. Again, those two are perfectly fine, but you can plug in 4. The square root of 4 is 2. So let's go to our graph paper and let's graph our square root function. At 0, we are at 0. At 1, we are at 1. At 4, we are at 2. If you wanted to even be more specific, at 9, we are at 3. So picture for me, our parabola that was here. Picture a parabola laying on its side where one side has not been drawn. Picture a parabola laying on its side where one piece of it has not been drawn. That's exactly what a square root is. It's technically x equals y squared, but using only the positive version of it. Okay, so that is our square root function. Get yourself a bonus point. Know that piece of information. Let's go to the absolute value, our last parent function for this set. There'll be further parent functions that come along the ride. I'll get you those when we need them, okay? Our absolute value function is f of x equals the absolute value of x, or y equals the absolute value of x is acceptable. Here is how you can get yourself a bonus point for that one. F of x equals, technically an absolute value is a piecewise function. What I mean by that is that if I plug in a negative, I have to do one thing, but if I plug in a 0 or a positive, I have to do something else. So it actually can be broken down into two sections. If I plug in a negative, so if x is less than, if x is less than 0, if I plug in a negative, I have to switch its sign. So that's why that piece is negative x. But if I plug in a positive or 0, I don't have to do anything. So if x is greater than or equal to 0, I don't have to do anything. I just leave the x value what it is. So that is a way to get yourself a bonus point by memorizing that piecewise function. If you take calculus in your future, we have to use the piecewise function to do certain types of new calculus stuff to it. So I like to introduce it in pre-calc so that you have that information, okay? Let's think about, do the same old, good old -1, 0, and 1. You can always plug in more values if you want them. 0 is the point or almost vertex of our V. We're going to get a V-shaped graph. If you plug in -1, you get +1. If you plug in 0, you get 0. If you plug in 1, you get 1. You might now recognize those same points from our quadratic. So those same 3 points right there. If we plug in 2, we get 2. If we plug in -2, we get +2, and 3, and 3, and 4, and 4. And you see that we get two pieces of a linear function, one with slope of 1, one with slope of -1. And so we get these two halves of a line that meet up at 0, 0. So that's the way I think of an absolute value. So all of these parent functions are functions you're going to have memorized so that we can transform them, so we can mess them up. okay? So on the quiz on Friday, I'm going to give you this exact paper, and you are going to give me the function. You're going to give me the graph, accurate to at least 3 points. You may put the XY chart on or not. It's helpful. And the little red pieces, you can get yourself a few bonus points, okay? So now let's go down to the bottom of this page. It says we're going to be transforming each of these parent functions, and we're going to graph them more quickly than we would have in a pre-calc class, okay, or in an algebra 2 class, okay. So hopefully you recognize, like our identity function, that this is just a line. And you are allowed to do whatever you want to a line. If you recognize that our slope is 2 and our y-intercept is the point 0, 3, that's a good thing to know, okay? So if I were to graph it, I would think about the fact that my origin or my spot, that 0, 0 spot has been moved up 3. So see how it's been moved up 3. And then my slope has changed. My stretch of the line has changed. So it goes up 2 over 1 or down 2 over 1. And you can go in either direction as far as you want. I am not a good line grapher without having a lot of points to go through. And luckily, Notability fixes a lot of the line for me because, again, not the greatest at drawing a line. What's nice about a line, you are welcome to plug in points. For any of these, you're welcome to plug in points. If you plug in 0, you get 3. If you plug in 1, you get 5. If you plug in 2, you get 7. You are welcome to plug in points. It's a line. So if you forget what it is, plugging in points is an option. Okay, so that's problem number 1. Now let's talk about number 2, okay? For number 2, hopefully you recognize that our parent is y equals x squared. And then let's talk about the transformations. Do you remember from yesterday, if we subtract 2, where does our, on the inside, where does our function move? 2 to the right. So we know this has gone 2 to the right. But what if we subtract 2 on the outside? What happens to our function? It goes down 2. So all we're going to do is take the parabola we learned a bit ago, and I'm just going to put those points that I know, okay? So not to muck up my picture very well. And then let's take those important parent function points, 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. We could do 3, 9, negative 3, 9, any of those points. And let's move them each down to the right 2 and down 2, okay? So if I move this point to the right 2 and down 2, I'm just going to move every single one of those points to the right 2, down 2, to the right 2, down 2, to the right 2, down 2. And I'm going to put my vertex where the vertex was, to the right 2, down 2, to the right 2, down 2. And that's the one we want to make our parabola. Because remember, our parent function is right here. So you'll see how by just knowing where the parent function lives, we can find where the new function lives and a pretty accurate graph of it just by moving the original function right 2, down 2. And take definitely the vertex and 2 other points when moving a parabola. It's not a bad idea. If you have 5 points, you're going to get a more accurate parabola. Okay, so that is how we can graph something very quickly. In a pre-calc or in an algebra 2 class, you might have plugged in points and, you don't have to do that anymore if you know what the parent function is and you know what the transformation is. So here, our parent is y equals x cubed. Let's put that on our graph. Okay, so we have those good points at negative 1, 0, 0, positive 1, positive 1. What transformation has occurred for problem number 3? It has gone down 1 because we have subtracted on the outside of the function. So just take those 3 good points, scooch them down 1 if you want extra points. 2 goes to 8, negative 2 goes to negative 8. You could add those on if you really wanted to. And then make your picture. So look at how quickly we were able to graph that. By recognizing that our parent was x cubed and that transformation moved the entire function down 1, bam, we got the graph. So see how powerful the stuff we did yesterday and the stuff we're doing today is together. Super, super important, okay? Let's move to 4. What's our parent function? What's our parent? Absolute value. I was thinking of the word V in my head. Let's make that on there. It goes through 0, 0, 1, 1, negative 1, 1. Put your V on there, okay? Make it dashed to show me that that's its origins, that's its roots, that's its genetics. It's going to be a V. But our V has been messed up. Let's talk about how our V has been messed up. Start from the inside, work your way out like order of operations. What does a plus 1 on the inside do to our function? The left. So that's going to go left 1. What does the negative on the outside of our function do? What does the negative on the outside of our function do? It does. It flips it. It flips it. It's going to flip it over the x-axis. So the values that are pointing upward is going to go down. So it makes it negative. So that 0, 0 point, let's move it to the left 1. That 1, 1, and negative 1, we're going to first point it up. So that would be if it just had a plus 1 there. But it's got that negative in front. So now let's point it downward. So our V has moved to the left 1 and flipped over the x-axis. You can put, as the more points you put in, the more accurate your graph is going to be. But 3-point accuracy is what I need. I don't know what Desmos is going to, or what iMath is going to do. Okay, let's move to question number 5. Question number 5. What's our parent? The reciprocal. The reciprocal is y equals 1 over x. It has a vertical asymptote at 0. It has a horizontal asymptote at 0. So our parent looks like this. What transformation has happened for number 5? We have a plus 2 by the x on the inside of the function. What has happened to our function? What does that plus 2 do to our function? It's going to the left too. So the heights haven't changed. The y values haven't changed. So this is our vertical asymptote. No, our horizontal asymptote. So our horizontal asymptote is still y equals 0. But our vertical asymptote has to move to the left too. So it is going to be x equals negative 2. So let's put that on there. So you first, I would say, anytime you have a reciprocal function, move the vertical asymptotes left, right, up, down first. Then we'll put on our points. So this point has to move to the left too. This point has to move to the left too. So our graph looks like that. okay? I know there's lots of little lines there, but our graph was picked up and moved to the left 2, okay? So pick up your asymptotes first. Any graph that has an asymptote on it, move that first before you move anything else. Let's take a look at number 6. What's our parent? What's our parent for this one? The square root function. How has it been transformed? So if we have a plus 3 on the inside, that is going to move it how? To the left. The minus 1 on the outside is going to move it how? Down, down 1. Okay. So let's put our original on. 0, 0, 1, 1, 4, 2. Pick up those important points. These ones right here. If you want more points, feel free. And just let's move them to the left 3 and down 1. So the left 3, down 1. Left 3, down 1. Left 3, down 1. Make your swoop to the right. Now, I would suggest, once you've graphed it, put that function into Desmos. Did it do what you expected it to do? Okay. But you, of course, need to be able to do it yourself. But it's a very important skill that we need to know how to transform functions. So we are done now with this one. You have to memorize your parent functions. The quiz is going to be Friday. I'm going to give you this exact paper, and you are going to have to duplicate it. Not the bottom stuff, just the first page. I am going to probably give you one like the bottom as a bonus point, but I want you have to know the front, those, what is it, 7 functions? 1, 2, 3, 4, 5, yeah. You have to know this page by heart. That is what is going to be on the quiz on Friday, okay? Okay, so turn that in, that is done. I know that's 5-3 day 3. We're gonna backtrack again, and let's now, could we open up 5-3 day 2? So could you open up 5-3 day 2 in Google Classroom, which is what you see here. 5-3 day 2. Please open this up so we can work on some transformation stuff, okay? So for problem number 1, it says, for 1 and 2, it says to describe the transformations necessary to transform the graph of f in blue, that solid line, into the graph of g of x, which is that dashed green line. Okay. So what I do when I'm asked to find a transformation and what happened, I usually will find if there's a vertex of some sort, I find it. Where did it go? Okay. And then I look at the endpoints. Are they pointing in the same direction? Because that's helpful to tell us if we've flipped, okay? So you'll notice that we have gone to the left 3, and that we have flipped up to down, so across the x-axis. So that's our transformations. So f of x is related to its parent, x squared. I'm going to show you 2 different things here. But first of all, we could say to flip it over the x-axis, we need to put a negative in front of, wait, I'm sorry, I have them flipped. G of x is our green function. Our blue function, we had to put a negative in front in order to flip it. And then to move it left 3, I have to add 3 on the inside by the x. I got a little ahead of myself there. So I need a negative on the outside. That is going to move it or flip it over the x-axis. I need a plus 3 on the inside. Okay. Now, if we actually wanted to use the function that is pictured, it is a perfect y equals x squared parent. So we could say that g of x is really the negative of x plus 3 on the inside of a square. Negative x plus 3 on the inside of a square, because our parent function is a square. Okay? A parabola, a quadratic, whatever you want to call it. Okay, so that's number 1. Let's take a look at number 2. In question number 2, so we have an absolute value. So our parent in blue is the absolute value of x. Okay. Now let's take a look at g of x. Now this time it has gone up 3, so it's gone up 3. But the slope that was normally 1 on this side, negative 1 on this side, see how the slope has gone up 1 over 2, up 1 over 2, up 1 to the left 2, up 1 to the left 2. So we have actually multiplied the function by 1/2 to do that. We've squished it down. So it's technically 1/2 of our f function. And we have to move it up 3. Oh, I'm okay. So your plus 3 would need to be on the outside. So if we actually applied this to our absolute value, it would be 1/2 the absolute value of x plus 3. And you could put in that function to our into Decimus, and you could see that it matches the green dashed line. Okay. Now let's take a look at question number 3. It says, describe the transformation necessary to transform the graph of f of x into that of g of x. So we have a negative 3 multiplied on the outside. So that negative 3 is a stretch upward and a flip. So it does 2 things when it's negative. So it's a flip and a stretch. This negative 1 on the outside moves it down 1. So all of these things are on the outside. They're always changing them up and down vertically. So it's going to stretch it vertically. It's going to move it down 1. Okay, so that is what the negative 3 does, and then the negative 1 is on the outside. Now for 4, if you took our cubic function, and if you throw a 3 on the outside, it's going to stretch it vertically. Now, if it was 1/3, it would compress it vertically. And the 1 on the inside here, we've added, so it's going to move to the left 1. It does kind of the opposite of what we expect. The center of my cubic has moved over to the left to negative 1. And that's a good way to, where's the 0 now? It's now at negative 1. That's a good rule to clarify in your brain where that center point has moved to. Number 5 through 8, we want to take the given function and we want to transform it using the words they've told us. So we want to expand it or stretch it vertically by a factor of 3. So we need a 3 out front of our function. And then we want to move it down 3. So we have to subtract 3 on the outside of our function. So both those things were happening vertically. That's why both of them are on the outside of the function. Number 6, we want to compress it horizontally by a factor of 2. Anything that's happening horizontally, we need to touch the x on the inside of the function. So we need to touch it by a 2. And you actually do the opposite of what you expect. If you multiply by 2, you actually compress it inward. Now, we need to translate it left. So now I'm going to take out my x. I'm going to put a little parenthesis there to hold it, that I need to move it left, so I need to add 3. So the 2 here is going to touch the x, and technically it would distribute, but that's okay. The x plus 3 is going to move it left. And take and throw in the original, throw in that new function. Is it squished this way? Is it moving to the left 3? And it would happen. This needs to expand horizontally. So expand this way. It's widening from left to right. So that 2 is not going to do what you think. You would think expand should be multiplication, but technically we need to divide by 2. But we need to translate it right. So now I'm going to erase it and put an x minus 1. That will move my function to the right. And then my whole thing needs lifted up 3, so I need a plus 3. Okay, so let's go over that again. If you expand horizontally, you got to divide by whatever you're expanding inside where the x is sitting. Translating to the right, put your x in parentheses and subtract on the inside. Translate up, add on the outside. So that would take our v. It would expand it out so it looks wider. It would move it to the right 1, up 3, and that you should picture a v doing that in number 7. Let's take a look at number 8. This time our parent function is the square root, swoosh to the right. We want to compress it vertically by a factor of 3. That means on the outside of our function, we need a 1/3. Okay. We want to reflect it across the x-axis, make that 1/3 negative. We want to translate it to the right. So on the inside of our square root, we want to have an x minus 2. But we want to move the whole thing down. So on the outside, we put a minus 3. So let's go over what that did again. If I want to compress it vertically, I need to divide by that factor on the outside of the function. The negative on the outside of the function will reflect it across the x-axis. I want to translate the function to the right 2 units, so I subtract on the inside of the square root, and on the outside, down 3 would be a minus 3 on the outside. Okay. Let's look at number 9. Write g of x in terms of f of x. So the first thing we need to know is that f of x is the square root of x. Now find your little starting point, that 0, 0, when I see a square root function. It has moved to the left 2. It has moved to the left 2. There's a flip upside down. But you see how it's kind of higher than it should be? That it's been stretched up. Let's look at how much. So I always pick this point. Should be 1. But do you see how now it's not 1 anymore? Let's see. So the next point that's good is this one. Was 3. I would bet that that is probably negative 1 2/3. So what is that? 3/3 plus 2/3, 5/3. I think that's probably 5/3. Okay. So this is a hard one, but the way that we're going to work it, we need to flip it so that it needs to be a negative on the outside. We have moved it to the left 2, so we need an x plus 2 on the inside. But we need some factor that will stretch it, and instead of at a height, it's hitting a height of 1, now it's hitting a height of 5/3. We're going to guess it's 5/3. So let's make that a negative 5/3. And again, if we throw it into Desmos, I would check at this point, are we getting this point? But I think that's going to work. Okay. Let's take a look at 10. Our parent function is what, guys? If you see that function, what do we know that the blue function is? What is our blue function? Can anybody tell me, what is that function? Kennedy, what do you got? Yeah, that's a cubic. One goes up and one goes down. It's half, it almost looks like half of a skinny parabola up and half of a skinny parabola down. So find the center point. And I think the center point is still, I think it's right there. I think. Okay. It has moved down one. So our g of x function definitely needs a down one on the outside. We haven't flipped it. The left end's still going down, the right end's still going up. But I notice that normally I would be hitting one. Do you see how I'm only hitting, I mean, something very small. And so I think that you have to divide by 8. Now here's why I think that. Normally this would be 2 over 8 up. Now I'm 2 over and only 1 up. So I think we need a 1/8 here. I think that would work. I'm not going to be focusing a lot on the stretch factors. Or if I do a stretch factor, I'm usually going to use either 2 or 1/2 so that you can start to visualize that. That's weird as to how that happens. The reason I think that is if I plug in 1, I think I get 1/8. If I plug in 2, I've only gone up 1 instead of 8. What would I have to multiply 1 by to, or 8 by to get it to be a 1 is 1/8. Now I think there are some functions where you could also have done, if you put x over 2 cubed minus 1, those two functions are equivalent. So if you thought that it looked like it was stretched outward by a factor of 2, do you see how it hits 2 outward instead of 1 out? Some functions, an outward and an inward, it kind of does the both things simultaneously. It squished it this way, but it pulled it out this way. So either of those, I would give you credit for it. Both of them mean the same thing. Okay. Some functions do that, especially some odd functions do that. Okay. Let's look at 11. So the first thing I always note when I see a function like this is where did the center of my asymptotes scooch to? So do you see how it went from 0, 0, it went up 2 over 1. So my blue function, which is our reciprocal, went up 2 and over to the left 1. So that's all what I first find. Where did my asymptotes move? And then I look at these points right here. They're in the perfect kind of 1, 1 away from there. But what has happened to the one that was on the right and the one that was on the left of our original? What happened to these? So this one flipped up, didn't it? And this one flipped upside down. So we need to flip it over the x-axis, up and down. Okay? So we need to put a negative on the outside. I usually just throw that up on the top there. On the inside, I needed to move to the left 1, so I need a 1. On the outside, I needed to move up 2, so put a +2 on the outside. So that flips it upside down. It moves it to the left 1 and up 2. So that's number 11. Well, I think we may get through this. We'll see. Number 12. Find where did the vertex move. That's where did the point move. It moved 1, 2, 3 to the left, 1, 2, 3 up. So 3 left and 3 up. My parent function is the absolute value of x. Do you see how the stretch is still 1, 1, 1, 1? So there's no kind of compression or vertical stretch that we have to worry about. But we do need to flip it over. So it's a vertical flip. Okay, so let's put all that together. This is our g function. So our g function is going to be -1. That's going to flip it over. X plus 3 is going to move it to the left. plus 3 on the outside is going to move it up. So I did not use an absolute value, did I? Goodness. How about if we do that again? So we want a negative on the outside, a plus 3 on the inside, a plus 3 on the outside. There we go. Like, well, I flipped it into a reciprocal, didn't I? Anyway, there is how we transform an absolute value. Okay. And then last two are almost done. 13 says to write an equation for this function. So we know that our parent is an absolute value. That's always your first thing. What is that? Who gave birth to that function? Then I always check that center point, whatever it is for that particular function, has moved over here to the right 2. And then let's look at the slopes of, I always do the positive side. It hasn't flipped over, but the slope is now 1 over 3. So our slope is now 1/3. So all that I do there is I change the slope to 1/3, and then I subtract 2 on the inside. We'll move it to the right 2. What can you do? Open up Desmos, plug that in. Is that the function you see there? If it is not, your function is incorrect. Okay. What's the parent for 14? The cube again. Okay, so we know we have to start with the cube. Find where the center point moved. It moved down 3. It still has a 1-1 relationship, but it has flipped over. So our new function is I need a negative on the outside. I need a plus down 3, so a minus 3 on the outside as well. So both of those things have happened vertically. That's why they're on the outside. So now please turn in day 2 mod. Now here's tomorrow. Tomorrow we're going to open up the homework. We're going to work on some homework together. You have a quiz over the parent functions on Friday. Please know that and prepare for Friday, okay?